Section 5.1 of your textbook introduces the topic of factoring algebraic expressions. To factor an expression means to write an equivalent expression that is a product. An equivalent expression of this type is called a factorization. Throughout Chapter 5, we'll discuss various methods for factoring polynomials. Let's begin by factoring some monomials. In each of these two examples, we will list all possible factorizations of the monomial using only positive integers as coefficients and exponents. First, let's look at the monomial 9x squared. Notice that the coefficient 9 has two factorizations, 1 times 9 and 3 times 3. So to organize our list of factorizations for the monomial, we can use these two factorizations. First, factorizations involving coefficients of 1 and 9. We have 1 times 9x squared. We have 1x times 9x. And we have 1x squared times 9. For factorizations using coefficients of 3, we have 3 times 3x squared. And we have 3x times 3x. Notice that we can't continue this list as we did the previous list and write 3x squared times 3. Because if we were to do so, we'd be repeating a factorization that we already have. By the commutative property of multiplication, 3 times 3x squared and 3x squared times 3 would be the same factorization. So the monomial 9x squared has 5 distinct factorizations. What about our second monomial, 12x cubed? Well, once again, let's organize our list based on the factorizations of the coefficient. We could have 1 times 12, 2 times 6, and 3 times 4. So we have 1 times 12x cubed, 1x times 12x squared, 1x squared times 12x, and 1x cubed times 12. We also have 2 times 6x cubed, 2x times 6x squared, 2x squared times 6x, and 2x cubed times 6. And then finally, 3 times 4x cubed, 3x times 4x squared, 3x squared times 4x, and 3x cubed times 4. 12 distinct factorizations. Now let's talk about factoring polynomials. The simplest method of factoring a polynomial is to use the distributive rule to factor out the greatest common factor of all the terms of the polynomial. Let's look at two examples. First, the trinomial 6xy plus 18xz plus 3x. Looking at those three terms, we can see that all of those monomials have a factor of 3x. So to factor the trinomial, we'll write 3x times the quantity, and then we'll use the distributive rule in reverse. So 3x times 2y would give us our first term of 6xy. And 3x times 6z would give us our second term of 18xz. And finally, 3x times 1 would give us a third term of 3x. So the factorization of our trinomial is 3x times the quantity, 2y plus 6z plus 1. What about the binomial in example 2? 5m to the 5th n squared minus 9m cubed n to the 4th. In this case, the coefficients have no common factor other than 1. However, the variable factors in common are m cubed and n squared. So again, using the distributive rule in reverse, we can see that the first term inside the parentheses would be 5m squared. And the second term inside the parentheses would be minus 9n squared. So our factorization is m cubed n squared times the quantity 5m squared minus 9n squared. Now there may be cases when we need to factor polynomials in which there is no greatest common factor other than 1 for all the terms of the polynomial. In such cases, we will factor the polynomials by a method called grouping. Let's look at the first example, 7x cubed plus 14x squared plus 4x plus 8. Note that for these 4 terms, there is no greatest common factor other than 1. So we will group the polynomial into 2 pairs of 2 terms each. First, let's look at the pair 7x cubed plus 14x squared. There is a greatest common factor for those 2 terms. It's 7x squared. Using the distributive rule in reverse, we can see that those 2 terms can be factored as 7x squared times the quantity x plus 2. What about our second pair of 2 terms? 4x plus 8. Well, those have a greatest common factor as well, which is 4. And again, using the distributive rule, we can see that the factorization would be 4 times the quantity x plus 2. How does this help us factor the entire 4-term polynomial? Well, now look at our new expression that we've written. We have actually 2 terms. Here's the first term, and here's the second term. And in each term, there is a common factor. The common factor is actually the binomial x plus 2. So we can once again use the distributive rule to bring that common factor out. So we have the quantity x plus 2. And then using the distributive rule, we see that first that x plus 2 is multiplied by 7x squared. And second, that x plus 2 is multiplied by 4. So our factorization is the quantity x plus 2 times the quantity 7x squared plus 4. Let's look at one final example. The polynomial 10a cubed minus 15a squared minus 2a plus 3. Again, there's no common factor for all 4 terms, so we can group the first 2 terms together, and we'll remove the common factor of 5a squared, leaving us with the binomial 2a minus 3. Now looking at our next pair of terms, we don't see a common factor other than 1. However, thinking ahead, we notice that we have that binomial 2a minus 3. So we want to try to factor this next expression, negative 2a plus 3, in such a way that gives us that common binomial that we saw before. So let's factor out negative 1, and then we'll see that we have negative 1 times the binomial 2a minus 3 will lead to that result, negative 2a plus 3. So we factored that pair of terms correctly. Now again, we see 2 terms. Here's the first term. Here's the second term. And they both have that common binomial 2a minus 3. So factor it out to obtain the answer, the quantity 2a minus 3 times the quantity 5a squared minus 1.